In this lesson, we're going to be looking at vertex form, and unlike some of the other times that we've looked at vertex form, we're actually going to learn a technique here that allows us to go straight to vertex form. So we've arrived at vertex form in the past by using symmetry, by using partial factoring, which is also a way of using symmetry. So now we are actually going to learn a technique for going straight there. When you look at an equation in vertex form, you might have noticed that you've got this factor squared. And this factor, because it's something in a bracket squared, so it's x minus h squared, all squared is the same as x minus h times x minus h. So that's the definition of a perfect square. We've got a factor squared. Now we've got some extra things here. We've got this a in front, and we've got this k on the trailing edge, but the cornerstone, the central part of a vertex form is this idea of a perfect square. So one of the key concepts, maybe the concept of this method called completing the square, what that means is to complete the perfect square that we've got. A perfect square can take two forms. There's either going to be a plus or a minus inside the factor. A plus b all squared has this form. A minus b all squared has this form. So what we're going to do is use the rules of mathematics, and in general we're going to use the rule that says that you can add or subtract 0. So if I have an expression, let's say x, and I add 5 to it and subtract 5 from it, have I changed it? I have not, because here those two together are equal to 0. So I can add or subtract 0, and if I want to, I can split that 0 up into different pieces. So we're going to be making use of that property for completing the square. Now, I'm going to start by illustrating this using algebra tiles, just to get you thinking about the idea of what do we mean by actually making a perfect square. So in this case, I have something fairly simple. I have x squared plus 6x, and since we know that we're going for a perfect square here, then I'm going to actually construct a square shape. I don't want that one. I actually want to put 3 of these down here. And so we ask ourselves, what can we put in this bottom right hand corner? And that's what we're asking here. What can we put in this bottom right hand corner to make a perfect square? And hopefully you can see that, but if you can't see it, you can fill it in. We can put in 9 single tiles to complete this. And now if we read our side, so first of all we put 9 tiles there. So that's what goes here, 9. And what do we have on the sides here? Well, this is x plus 3. This is x plus 3, so plus 3. So if I had x squared plus 6x, the thing I would need here to make it a perfect square is plus 9, and here's what that perfect square would look like in factored form. Let's take a look at a second example. We've got an x squared. We've got minus 4x. So here's something else I want you to notice. Negative 4x, because we're working towards a perfect square, I know I need to have an even number of those on each side. So I'm going to take half of negative 4, gives me a negative 2 over here and a negative 2 over here. But negative times negative is going to be positive, so I actually still end up with positive tiles here in this corner. So that's something else that's noteworthy. So one thing is I took this number negative 4, and I divided it by 2. And this, so negative 4 divided by 2, that's negative 2. And notice that I have an x here and an x here. This negative 2 went here and down there. And so our answer here is plus 4, and our answer inside the factor is negative 2. So this idea of this taking the x term, the coefficient from the x term, and dividing by 2, we're going to make use of that as well. Okay, so what's missing from these perfect squares? Now we're going to try to do it without without the algebra tiles, but we can immediately make use of what I did before, which is this middle coefficient is positive 10. I'm going to divide that by 2, and of course that gives me positive 5. Normally I wouldn't write the positives, I'm just doing this here to make that really clear. Okay, so positive 5, that's going to end up going in here. So this becomes x plus 5. And what we put, so this just went directly. What we put here is positive 5 squared, because this has to be a perfect square term in the front, and we need a perfect square term here, so positive 5 squared is 25. And if we look back at our other examples, we ended up with a negative 2 here, a negative 2 here. What is negative 2, or this negative 2, all squared? Positive 4. If we look at this one, positive 3 squared is 9. So we've got this pattern. We take this term and we divide by 2. And then the result of that goes into the perfect square bracket. And if you wanted to write it outside in the expanded form, you would square it and put it there. Let's take a look at a second example. I'm going to take this number, which is negative 18. I'm going to divide it by 2, and I end up with negative 9. I take that number, negative 9, and I can put it straight into this bracket like this. Or I can take that negative 9 squared, all squared, which becomes positive 81. Notice I'm not even given the option for a sign here. A perfect square trinomial, the only place where you can have a change in the sign is this second term. That's assuming, of course, that the first term is positive. That's one of the reasons why we like to write it that way. So if the first term is positive, the second term can be positive or negative. This positive and negative is going to be reflected on the sign inside the bracket, but this number outside is going to be positive. Now, what if we wanted to do a question like this using an area model? We don't have tiles, but we like working with the area model. X squared, and then I take this negative 18x and I divide it in 2. So that's negative 9x here, negative 9x here. And so you can already see from this, I've got an x minus 9, an x minus 9, and negative 9 times negative 9 is positive 81. So this area model works just fine for doing this as well. Now, we haven't actually done any completing of the square. We've just identified what was missing. So these are already assuming that these are actually perfect squares. Now, what if we have something a little bit more along the lines of what we want to develop today? I have an x squared. I have positive 6x. So 6 divided by 2 is equal to 3. So I know I need 3. 6 divided by 2 is equal to 3. Let's try that again. I need 3 of these on each side. 1, 2, 3. And 1, 2, 3. Now I already have 3. So I have 1, 2, 3 provided, but that's all I'm allowed to use. That's it. This is what I have available. So now we're going to make use of the idea of adding and subtracting 0. Because you can see I actually want some more red tiles here. The only way I'm allowed to do that is for every red tile I bring in, I also have to bring in a negative tile to offset it. And I'm just going to put that negative tile off to the side. So bring in a red and bring in a blue. Bring in a red, bring in a blue. So I brought in 3 of each. So I need to bring in 3 more. Okay, so I've brought in my extra tiles. So this is equivalent to all of this together because of these offsetting tiles. So what is this part equivalent to? This is an x, this is a plus 3, this is an x, this is a plus 3. So there's the perfect square part. Now I also have to take into account this whole picture. So not only do I have my perfect square, but because of my little trick with adding 0, I also have negative 6 here, so minus 6. If you take a look at that, that is actually vertex form. So this has vertex, in this case, at -3, -6. So those leftover tiles are important. Okay, so this one, x squared, -4x, so I'm going to take half of them and put them on this side. And I'll take half of them and put them on this side. Now what do I want here? I want negative times negative. I want blue tiles here, but in my original expression I just have three, sorry, I misspoke there. I want red tiles here because this is a negative, this is a negative. I want negative times negative to give me positive in this corner. But I have -3 tiles to start with. So the same thing we did before. If I want to bring in a blue, I have to bring in, if I want to bring in a red, I have to bring in a blue. If I want to bring in a red, I have to bring in a blue, red, blue, red, and blue. Here is my perfect square. X minus 2, x minus 2. This is x minus 2 all squared. That's this shape. And then we've got this extra 1, 2, 3, 4, 5, 6, 7. And there we go, vertex form. That is completing the square. Because when I started with my shape here, I didn't actually have a square. I had to bring in a positive one and a negative one. I bring in a positive one and a negative one until I could complete this square in the corner. That's what completing the square refers to. You're completing what you need to make the perfect square. So let's see what that looks like algebraically. Some general advice on how to do this. If you happen to have, now when I use algebra tiles, I don't normally include anything that's a complex trinomial just because it gets unwieldy to move the tiles around that much. But if you happen to have a leading a term, you're going to factor that out from the first two terms. And seeing that will help you understand it. Then we're going to force a perfect square for, again, the first two terms. So you can see we're going to be focusing on them and then collect the constants at the end. For a simple trinomial, this is quite straightforward. So to complete the square, factor out an a from the first two terms. I don't need to do that. That step is not necessary here because my first term just has a 1 in front. Force a perfect square for the first two terms. Now I'm going to show that here over with an area model, what that might look like, and also I'm going to just do this algebraically. I'm going to do both. So I'll start by doing this one algebraically. So this is equal to x squared plus 12x. Now to make a perfect square, what do I want to do? I want to take this middle term, 12, I want to divide it by 2, and that's equal to 6. And then 6 squared goes here. So what is 6 squared? That's equal to 36. So this gets plus 36. I think I'm going to move that out of the way. Move that up here. Okay. Now don't forget, I just added 36. I just made 36 appear out of nowhere. Let me change colors here. Because my original expression was x squared plus 12x minus 7. So what I'm going to do is I'm actually going to make room here, and I'm going to put plus 0 here. Is that allowed? Sure, I'm adding 0. But I don't want to actually add 0, I want to add 36. What allows me to add 36 is to add 36, I have to also take away 36. And this is the same as adding 0, which is perfectly legitimate. But because I've done this, I've got in these first three terms, I actually have created a perfect square. So now I'm going to look at this in two different pieces. The first piece is x squared plus 12x plus 36. Now if you need to, you can go over in some rough work and you can factor that. Or you can use what we've been talking about, which is this is the same as x. I see a plus sign here, so that's going to be plus, and it was 12 divided by 2 gave me 6. So this is x plus 6 all squared. That's this first piece. And this second piece is negative 36 minus 7, which is equal to negative 43. And there we go, vertex form. We've done that by completing the square. What would that look like over here? We would start with our first two terms, x squared, and then we would take this 12x and we'd break it up into a 6x and a 6x. And don't forget, we've got a minus 7, and it's usually a good idea just put the minus 7 outside. So the minus 7 gets kicked outside of the box just to begin. This is x plus 6. This is x plus 6. But because I've got a 6 and a 6 here, now remember, what I've drawn in here is all I have. So if I now bring in a 36 here, I have to also subtract 36 because these two that I got marked in red have to total 0. So if we take a look, you can see I've got my x plus 6 times x plus 6, that's x plus 6 all squared, minus 43, which is the sum of those two. That's the collecting the constants step. Okay, so here I did, let me just label these. This is step number 2, and this was step number 3. Let's take a look at another example. Another simple trinomial. I'm going to start with the area model this time. So I will put an x squared here. I've got negative 20x, which means I put negative 10x there, negative 10x there. So this becomes x minus 10, x minus 10. And we've got plus 15 sitting out at the side. Negative 10 times negative 10 is equal to positive 100, which means I need a negative 100 to balance those. And so my result from this, you can read it right from there, is going to be x, let's go back, it's going to be from the edges, we've got the perfect square of x minus 10 all squared, and then we've got positive 15 minus 100 is minus 85. Or, and the reason I didn't just write this answer up here is because I want to show you this algebraically. So we get y equals x squared minus 20x, and then we've got this plus 15, which I'm going to write over here, because what I've done is made room for, well, what do I have to put here that's equal to 0? So I've got a negative 20 here, I have negative 20, and I divide that by 2, that's equal to negative 10. Negative 10 all squared is equal to positive 100. So this becomes plus 100 minus 100. I look at these first three terms. They are my perfect square. So these three terms together become x, and it was minus 10, so it becomes minus 10 in the bracket, all squared. And then these two terms, negative 100 plus 15 is minus 85. Y equals. So there we go, exact same answer as I had before. Now we're introducing, in this case, a complex trinomial, but remember, we're not solving the whole trinomial here, we're just changing the form. In particular, we're looking at the form of the first two. So what we want to do now, y equals, is we want to factor out whatever a is. In this case, a is equal to 3. We want to factor that from the first two terms only. We're not factoring, we're not doing partial factoring here, or factoring by grouping. I don't want to factor out the x's. I am only factoring out the constant 3. And that gives me x squared plus 4x left behind. And then plus 11 is on the outside of my bracket. That is equal to 3 bracket x squared plus 4x, and now I need to leave myself, I'm going to leave myself a nice big chunk of room. I don't normally draw the bracket first, I'll just do the work, but I want you to see that what I've written so far is exactly the same, except for I've got this odd space I've left here. And the reason I've left that space is so we can look at this 4. So 4 divided by 2 is equal to 2, and 2 squared is equal to 4. So the squared is what goes here. We add the squared value, and we subtract the squared value. And then we've got whatever's on the outside of that bracket. Now this is a little bit more complicated than it was before, because what we have here is our perfect square, but our constant, one of our constants is still in this bracket. And this constant has to be multiplied by this constant, by this a value, in order to join up with this one. So I'm actually going to take a little bit more time with my steps here. I'm just going to write out this perfect square. So that is x squared plus 4x plus 4 is the same as x plus 2 all squared. There's a minus 4 on the end here. There's another bracket. Actually, I'm going to use a square bracket because I don't like having a round and a round. So a square bracket. So I've replaced this outer blue round bracket with an outer blue square bracket. There's a coefficient of 3 in front. There's the 11 on the end. And now what I'm going to do is I'm going to multiply this 3 in front of that bracket, and I'm also going to multiply the 3 times that negative 4. So we get y equals 3 times this bracket. I'm not expanding this bracket, I'm just getting this coefficient in front of it because I'm looking for vertex form. X plus 2 all squared. 3 times this bracket, 3 times this bracket. 3 times negative 4 is negative 12, and then we have a plus 11. And last step, simplify. 3 x plus 2 all squared minus 12 plus 11 is minus 1. If I wanted to use an area model for this, it still works, but it's a little bit more difficult because you still want to factor out your 3 first. And then you can do your area model on what's inside. So there's a little bit more organization, and I think this still points to the fact that even though algebra tiles and an area model are useful tools, they are not as versatile as a pure algebraic representation. So x squared plus 4x would be plus 2x here and plus 2x here. And so what I need to do is just complete the outer part, or sorry, the inner part. So this becomes x plus 2, this becomes x plus 2, and then 2 times 2 is 4, but I have to put a minus 4. And you can see we've got this here. So this inner bracket, this basically, using the area model, I'm able to make this square bracket. It's an x plus 2 all squared minus 4. But you still have to worry about this coefficient in front, and you still have to worry about this constant on the end. So an area model here is far from ideal, but it does help you with the interior stuff. Okay, now what about if we have a negative sign? The same idea applies. We're going to factor out the negative sign. So I'm going to factor out a negative 1, and I'm only factoring that from these first two terms. So that becomes negative 1 x squared minus 6x. And then we've got this plus 13 outside. So y equals negative, I'm not going to keep writing negative 1, I'm just going to put a negative in front of that bracket. X squared minus 6x, I'm going to put something and something here, and then I've still got that plus 13 outside of the bracket. So what is my middle value? It's negative 6. I'm going to divide that by 2 to get negative 3. And then negative 3 all squared is equal to 9. So I write a plus 9 here, a minus 9. It's always plus 9 first, and then minus 9 to make it equal 0. I'm going to find the perfect square that matches those first 3 terms. And so that's going to be, we had a minus 3 here, so it's x minus 3 all squared and then we build the rest around it. So we had this round bracket. Again, because I'm going to have double brackets now, I make this square. There's a negative sign in front. Then we have a -9 inside that bracket and a +13 outside that bracket. Now multiply this. Don't forget it's -1, so I'm going to multiply this in front of this bracket, and I'm also going to multiply it by that -9. So we get y equals -1 times this bracket is just negative of that bracket. -1 times -9 is +9 plus 13, and the last step, negative bracket x minus 3 all squared, and this is going to be +22. For this one, I'm not going to bother with the area model, but you would do your area model on x squared minus 3x minus 3x. I would take this -6x, but I do it on the contents of this bracket. So if you're going to use the area model, you have to factor out the a value first and then apply the area model. And that's it for the lesson. A bunch of techniques there, and really focus on getting yourself to the point where you can apply the algebraic technique, because as I hope I've shown you, that's the most useful of them.